Welcome to the lecture 10, scattering parameters and impedance matching part 2. So we've done part of the L network impedance matching in the last lecture. So we'll be taking a step ahead and doing a little bit more some of the examples and the different types of impedance matching in this course, in this lecture. So we briefly talked about what is expected out from the impedance matching. So the impedance matching network that we introduced has to do two parts basically. It should show the load looking into the source side impedance, a conjugate of load impedance. So the idea is that so it should see RL minus JXL. So the imaginary parts cancel out and it presents the same impedance as the load resistive part, so you get the maximum power transfer. So for the impedance matching, looking into the input impedance match to get the maximum power from here to here, this point looking into the source should also, so RS plus JXS, look from the source side, that's the source impedance, should see looking into the impedance or towards the load side, should see RS minus JXS. So that it matches here, it gives a maximum power transfer, so that's the impedance transformation, and then it shows to the load, it only sees RL minus JXL. So that's the basically the background on the impedance matching. So what we're trying to achieve. So we did a very simple example, I think last week lecture, where we matched to a pure resistive load. Now today we do another example. So this is to design impedance matching network between the below shown source. So source is 50 ohm and the load is 500 ohm. So obviously load is greater than source resistance. But the important part here is the load here is not just resistive. It is also has a capacitor in series. So it has some imaginary part to the load resistance. So load resistance is R load plus JXL format. Okay. Now let's see how we solve this. Now obviously we need a matching network here, and first thing is that we need to figure out what's the topology of that. So it says it needs to block the flow of the DC. From last week, if you remember, we had a couple of configurations, but if you want to block the DC, we need to have a capacitor here, and then we need to have an inductor. So this is a topology when you have RL greater than RS and DC blocking. So if you want to satisfy both these conditions, this is topology we need to choose. So we have to find this capacitor, we need to find this inductor. Now the first thing always starts with finding Q. Q is given by RL over RS minus 1. Now in this case 500 over 50 minus 1, so that's 3. So Q is given. So the other design equation is Q equals XC divided by RS equals RL divided by XL. So if you want to find XL, which is the reactance of that inductor, so XL, so we can get, say, Q equals RL over magnitude of XL. That means 3 equals resistance of the load is 500 over XL is pretty much omega L, right? So if you get L is 500 divided by 3 divided by 2 pi, F is 1 times 10 to the power 9. Now when you solve that, you get 26.5 nanohenry. Now same way, if you want to find XC over RS equals Q, now XC is 1 over omega C, RS equals Q. So you get C as Q, 1 over Q omega RS, and when you solve that, C will be 1.06 picofarad. So that means you have for here 1.06 picofarad, and for here you have 26.5 nanohenry. Now when you do this transformation, you only consider a purely resistive load, you didn't really consider about this capacitor. Now, ideally, you would want to cancel this capacitance out by a equivalent, as with a parallel inductor here. So basically, we want to cancel this capacitor, which is 10 picofarad, with another inductor in parallel. So they cancel out. So it only sees the real part of that impedance. So this inductor, if it cancels out, it needs to resonate with the capacitor. That basically it says omega squared equals 1 over LC. Or you can just look at the impedance given like the reactor. You can look at the reactance of that, then make them equal. So you end up with omega squared. So equals 1 over LC. So L is basically omega squared C. So that means 1 over 1 times 10 to, so 2 pi f, right? 10 to the power 9 squared, 4 pi squared times C is 10 picofarad, 10 to the power minus 12. And then you will get an answer for that as L equals 2.53 nanohenry. So basically we want a circuit that has capacitor, inductor, 26.5 nanohenry, and then another inductor which is 2.53 nanohenry, and then this capacitor 10 picofarad. So this is the load side, and that is the the capacitor is not the part of the source. From here onward, that's the source. So that capacitor and the inductor cancels them out, but you can't include that as part of circuit. So you need to combine these two together to form your circuit. So you have a capacitor which is 1.06 picofarad. This is double part of my monitor as a tablet. So you have to have 1.06 picofarad, and then combine these two with one inductor, and that forms your matching circuit. So when you combine these two, that's basically, say this is L1, this is L2. So total inductance L is L1, L2 over L1 plus L2, right? So that way you can figure out the L value, and you sub them in, you will get somewhere around I guess 2.3 nanohenry value. So that will be your total final circuit, that is 2.3 nanohenry. So that's your matching circuit. So this is straight an example from the STS book. I think it is, I can't remember the example number, but you need to go through it, and then you'll find that's a straight example from the STS book. So go through it, you get similar question or use the same concept, similar concept in your exam question. So, and I will do one more question of this type in the lectorials. So we noticed that the bandwidth of a matching circuit is a critical factor, because matching circuit can't be infinite bandwidth. So they can't provide impedance matching for a very large bandwidth. That's because the energy storage part by the inductive or capacitive part elements limits its resonance bandwidth. Now, Fano, basically the Fano body limits provide the fractional bandwidth, which is this part. So bandwidth over the resonance frequency is called the fractional bandwidth for different types of configurations: RC load, parallel RC, parallel RL, series RL, series RC. Now, these equations you don't need to remember, because you can use them directly. Just keep a copy of that for your exam. You can simplify them to two different parallel loads and a serial load. So these two are parallel loads, these two are series load. So basically it says the fractional bandwidth is proportional to your Q, is inversely proportional to your Q. So these two can be simplified to this. So the fractional bandwidth here is proportional to your Q factor. So the higher the Q, you get a smaller bandwidth. So that means if you have more inductive capacitive elements in a circuit, you tend to have, if they're more reactive parts, you tend to have higher Q. That means you get a certain good rejection, but then you have very small bandwidth. So if Q is not equal to 0, that means you will always get some sort of a reflection, because therefore tau average, which is the reflection coefficient. So tau average is actually the reflection coefficient over the band. The average value of the reflection coefficient over the band cannot be 0. So for example, if you think about Q being 0, so this goes to infinity, right? This goes to infinity. Now Q being 0 means it's purely resistive. So Q goes to infinity means you can have a extremely high, pretty much infinite bandwidth. Now for that to happen, you need to, so you can do that with the transformers when you don't have inductive or reactive loads. But in practice, you will always have a reactive component in the load. So we can't have infinite bandwidth. We can do different tricks, but we can't really have a infinite bandwidth. Now, remember if you from our previous discussions that our L matching circuit had a certain Q given by RL over RS minus 1 square root. So that Q is fixed. So we can't really change that Q, and that determines its bandwidth. So higher the Q, narrower the bandwidth. So from your previous Q, you might remember this formula, RL over RS minus 1. So this Q is pretty much dependent on RL and RS. So if you have a load and a source resistance, you don't really have any control over Q. So the bandwidth is fixed for that. Now, there are ways to overcome that by designing the impedance matching circuit. This is only for L network matching, right? In a slightly different way. Now that's what we're going to look into in the next one. So the multi-element matching is a way to have a control over Q. Now, when you have multi-element matching in a T network or pi network, so you will have two L networks back to back. So this is a L network, this is L network, and they are back to back. And in a pi network, so this has a shape T and this has a shape pi, and that's why they're called T network and pi network. So a pi net, you can always convert in between them. So you can convert a T network to pi network and a pi network to T network. We are not going to talk about that. I think you may have done it in your previous courses. Now these X1, X2, X3 are impedances, actually, so they are reactive components. Now, for example, so these things will give you a bit more control over Q, but so the Q in this case for a T network is given by this formula. Now what they do is they introduce another term called RV. So the RV is a resistance that you introduce in between those two back-to-back L networks. So if you think about this part, this is an independent impedance matching network. You can use the same formulas that you used before, if you remember, L network. So based on RV being larger or smaller RVs, if RV is larger, you have a set of equations and then you can pick the topology. And if RV is smaller, you have another topology. And then you can also design this part considering this as an independent L network matching circuit. So you use the same principles, same equations that we use, but you segment the T network into two different L networks back to back. Now, but the downside of this T network or pi network is it results in a higher Q. It gives you control of Q, but it's always a higher Q in the T network and pi network. As a result, because of higher Q, it results in a narrower bandwidth than L network. So it didn't really help us to improve our bandwidth. It actually narrowed it down. Now the pi network is same. So that I suggest you to read the STS book on this, and then also go through the example they've given in there in designing. So design a pi network to match 50 ohm to 500 ohm. Decide Q is state. So in here, you can design the Q to be 10, by picking the RV, right? So that's a way of, so it gives a little bit of control. Now you might find that in the STS book, the example, it shows 4 configurations, 4 matching networks, 1, 2, 3, and 4. So this is pretty much the same matching network. 4 matching networks to that you can have to match a 50 ohm to 500 ohm. So 50 ohm source to a matching network to a 500 ohm load. So this circuit impedance matching network can be this, or that, and or that. So go through that example in the STS book. This gives you a lot of control. Now, depending on what you require, for example, you might need to eliminate stray reactances. For example, in the last, so if the load has a reactance, you may need to cancel it out. So maybe you pick a better, you might pick something that's easier for you to work with based on the reactance value of the load, or you might need a low pass or a high pass. So for a low pass, you need inductor. For a high pass, you need a capacitor. So you might pick one of these two based on that. And also you might need, DC block in the input stage and then not short the supply. So you might use that. So depending on what your requirement, you might choose which impedance matching network you need to use. So we won't have to go through each example in detail because of the limited time. So it's your duty to go through those examples, and that'll, it's also good for you to work it out. Okay, so now even T-network, pi network, you'll notice that it doesn't really help you with increasing bandwidth. It only reduces your bandwidth because it has higher Q. So there are other techniques such as broadband matching. So instead of having back-to-back L networks, it has cascaded L network. So this is one L network and this is another L network. So in this example, the load is smaller than source, but you can also have the resistance of the load larger than source. But what you do is you again segment it to known set of, so this is one L network. So introduce a third resistor in between, and that's another L network. So you can handle this part from the design formulas you know already. Now the beauty of this is to get the maximum bandwidth, you have to satisfy this condition, Q1 equals Q2 equals this formula. So the Q1 is the Q1 of this circuit, Q factor, and the Q2 is that. So you need to have each of those Q equal so that you can get the maximum bandwidth. So you have from here, if you remember, the Q is given by R divided by R minimum. That's the R minimum of this circuit minus 1, R max or RV. So R min can be the minimum of resistances of RL, comma RS. So R max is the maximum resistance from RL or RS. So depending on that, you decide what is your configuration here. But regardless, this is your RV. Now, once you do that, you will get a Q that is, with a better control and higher bandwidth. So that's an example. Go through the example in the recommended text. And this can also be done for multiple segments. So you can have multiple segments like that. Then you can make sure that each Q of those segments are equal. But what you see in general is that your basic L network matching theory is very critical. Once you know that, you can apply that for T network, pi network, or broadband low Q matching technique. So regardless of your network topology, your basic building block is L network matching. So get familiar with that. Do more exercises. Now the next part that we are going to go through is through the Smith charts. Now for that, I'm going to use some of the older contents that I've done in the last year. So from here onwards, that recording that you will see is from the last year, but it's the same content. So I think it's nothing much. Even if I do it now, I'll probably repeat the same. Today we'll start with the Smith chart. Now the Smith chart is a graphical
graphical tool developed by a scientist or engineer, you would say. That tool, so his name is Philip Smith. That's obviously where the name came from, Smith. It's a very useful tool when you really do a lot of designs on the MMIC side, or like anything on the microwave antennas. It's very useful. Now there's a lot of there's a proof on like how to come up with this graphical tool. So there's a lot of mathematics behind it. I'm not interested in teaching you that mathematics because it's probably informative to have but not very useful when you do the design, right? I will show you the highlights. Now in the Smith chart, you can represent any passive impedance admittances in this chart. Now you'll notice, so there's lines, there are lines like that, right? And there's the horizontal line across the diameter. Now this point is infinity, this point is 0. I'll talk to you what that means. In here I think there's a typo. This should be infinity, this should be 0. Now at the moment we'll focus on the Smith chart on the left. This is called the Smith chart. So this horizontal line is called the real impedance axis, which means it's a resistance. Now in the Smith chart you can draw a point, and that point has a certain impedance. So that impedance, if it's impedance, has a real part and an imaginary part, right? So the real part here is on this horizontal line, on this line. The imaginary part can be on both sides of this horizontal line, so it can be in the upper semicircle or the lower semicircle. Now when you actually pinpoint an impedance, you have to normalize that impedance. So for example, if I have an impedance, say 10 plus 20J, before you represent that on the Smith chart, you need to normalize that, which means you need to divide it by the reference impedance, which is 50 in our case, right? So which means it's 20 divided by 50 plus 20J divided by 50. Now, so this comes up to 0.2 plus 0.4J. Now that coordinates, you can represent it on this circle. Now before we represent something complex, we'll just represent just a resistor. So assume you have a 50 ohm resistor, and if you want to represent that in this Smith chart, so this is the impedance. So if I normalize it, it will be 50 ohm divided by 50 ohm, right? So that is 1. Now that 1 means, so it's actually reference impedance. It's normalized reference impedance, which is 1. It's in the real axis, you will see the 1, and that's 1. So anything that's 50 ohm reference impedance, which is 1, will be in the middle of that circle, and it has a 0.1, right? So when you read off that, so it's actually 1 plus 0J, right? So the 1 is the real part, and that's on this horizontal line, it's 1. Now if I want to represent 100 ohms, so I'll read that. If I want to represent 100 ohms, I divide it by 50, it's 2, that will be here, right? Now you might have a lot of questions now, what happens upper circle, lower circle, we'll come to that slowly. I'm teaching this without teaching you the mathematics behind it, so it's somewhat harder, but if I teach you mathematics, you might not come to this stage anyway. And you just have to know the outcome, I think, at the end of the day. Okay, so if I have 200 ohms divided by 50, it will be 4. That's here. So what will be at this point? That will be infinity divided by 50, right? Right? So that will be infinity. that means it's an open circuit. Open circuit will have infinite resistance. So that's an open circuit end. Open circuit. Now let's try to go to the left hand side of this, go towards this side. So if you have impedance as 25 ohms, if I divide by 50, that's 0.5, that's this point. Likewise, if I go towards the left, if I have 0 impedance, it's a short circuit, divide by 50, that's 0, and that's here. So this is a short circuit. So now we at least know how to mark points on the real axis, right? So what we don't really know at the moment is how what comes up in the upper hemisphere and the lower hemisphere. Now, you'll see these circles, so they represent a reactance, all these circles. So you have 0.25J, 0.5J, J, 2J, 4J. In between them there will be lines, it's just that it's not drawn. So in here there will be 0.375J. So you can actually dissect it and have multiple of those lines. Okay, now say I have, so this circle that goes through 1 is called a constant resistance circle, right? So it not only goes through 1, the 2 has a circle like that, 4 has a circle like that, and 0.5 has a circle like that. So they are called constant resistance circles. What it means is if you are on that circle anywhere, mathematically it can be proven the real part of your impedance is always 1. So if you are here, your impedance, the real part of that impedance is 1. If you are here, it's 1. If you are here, it's 1. If you are here, it's 1. The real part of the impedance. So that means it will be impedance normalized 1 plus j something. When x is 0, you are here. When x is something else, you are here. So as x increases, you'll move that way. As x becomes negative, you'll move this way. Right? So you will move this way if it's negative x, positive x. Just it deletes itself. It's positive x. Okay, it will move that way. Now, so now let's see if I have a normalized impedance of 1 plus 0.25J. So the real part is 1, right? So I'll delete this. So real part is 1, so I have to be in this circle somewhere. My reactance, so this is the resistance, that's the reactance. The reactance is 0.25. Now this curve here represents that curve represents reactance. So it's 0.25. So this point has a real part of 1, reactance of 0.25 J. Okay, so same way you'll have here 1 plus 0.5 J, here it will be 1 plus J. Likewise you can represent any impedance which has a real part and an imaginary part on this circle, right? So I was talking about, all the time I was talking about 1, which is 50 ohms. Now assume, so this is quite new to this, first time I guess you guys are learning Smith chart, right? So I'm trying to take it very slowly because it takes a while to absorb it, right? Now say you have a normalized impedance of, so not a normalized impedance, impedance of 25 plus 50J. And I want to represent that on the Smith chart. how would I do it? I will have to get it normalized first, which is 25 plus 50j divided by 50 gives me 0.5 plus 1j. Right? So I'll look at the real part, 0.5, and I'm here. I should be on this circle somewhere, and it's 1j, which is here. So this represents 0.5 plus 1j. Okay? Now, you can imagine there'll be, if I want to get 0.5 plus 0.125j, it will be somewhere here, which I don't have the curve, but a proper Smith chart will have all these curves. So it's very crowded with curves. Now, what does it mean if you have a positive reactance? That means it's inductive, right? So if you guys remember, you have a inductor will give you your positive reactance, j omega L, which is your XS. If you have a capacitor, it will give you a negative reactance, j omega C, 1 over j omega C, or you can say it's minus j over omega C. So anything negative will be a series capacitance. So now for the same example, if I have said that as 25 minus 50j, and if I normalize it, divide by 50, I get 0.5 minus 1j. So I'm on the same circle, but I'm down here. So this represents a 0.5 plus, sorry, that's wrong. So here, right? So this represents 0.5 minus 1j, right? And if I'm here, it represents 0.5 plus 1j. So it actually looks like if I have a resistance, so let's say if I have a resistance 25 ohms and an inductor which gives me an excess of 50 ohms, if I'm looking in here, my impedance would be 25 ohms plus 50j, right? So that's what I say. And that can be represented on the Smith chart here. Okay? So this is quite early stages of Smith chart. We are just trying to represent points, represent impedances on the Smith chart. Okay? So likewise, you can imagine you can represent pretty much any impedance here, right? So if you have like 500 ohm plus 200j, if I divide by 50 and normalize it, it will be 10 plus 4j, right? So that means 10 is probably here, and it will have a circle itself, and the 4j it's probably somewhere here. So the higher the impedance, it will come towards this end. Shorter the impedance or smaller the impedance, it goes towards that end. So that's representing the impedance on the Smith chart. So this is called the impedance Smith charts, because I was always dealing with impedances, right? So the same way you can represent admittances, which is on this circle. So you'll notice that what's changed here, let me clear this up. What's changed here, the circles came to the left hand, right? And then the curves now goes negative here, negative here, and this becomes positive, and it's increasing this way, and it's increasing this way, whereas here it's increasing that way and then increasing that way. When I said increasing, maybe I should. So reactance here is 0.25j, it's 0.5j, j 2j. So that's what it's increasing. So if you travel along the constant resistance circle, you will notice when you travel towards the right hand side or clockwise, you will increase reactance. If you travel anti-clockwise, you will increase negative reactance. Okay. Now the same way when we represent Zn, you can represent Yn which is 1 over Zn in the Smith chart. Now, if you look at your AWR projects, which I'll show you later, you will only have Smith chart like this. You won't have this admittance Smith chart. But if you get like a old textbook, you will have both of them overlap together as shown here. So you have circles for admittance, circles for resistance circles, and these are called conductance circles. Right? So if you have a impedance, you have R plus JX, right? This is called resistance, reactance. Then you have admittance, you have conductance, and then susceptance, right? It's called conductance, this is called susceptance. I don't know how to spell it actually. Susceptance. So somehow you have G plus JB. Now with the G is called the constant conductance circles. They are similar to constant resistance circles, which is here. Conductance circles are on the left hand side. The susceptance lines are the lines shown like this. Okay, so we'll try to. So you might be wondering why, like, you represent both of these circles in one. We'll try to do a question, might be useful. Okay, so the question is convert impedance 50 minus 50J to admittance. So if you have to do this, usually you have impedance Z equals 50 minus 50J. Right? So how do you find the admittance? You'll do Y equals 1 over Z, right? So which means 1 over 50 minus 50J. Which means, so you can actually times both sides by 50 plus 50J to get rid of, it's called the conjugate. So you multiply it by conjugate. So you get 50 plus 50J, divide by here it's 2500 minus 2500J squared. So J squared becomes minus 1, which means it's 5000, right? So it becomes 50 plus 50J divided by 5000. So divide by that, 1 over 100 is 0.01 plus 0.01J. That's your admittance. So the answer to this question is, if this is impedance, your admittance is 0.01 plus 0.01J. So that takes us a few steps to work it out, right? Now you could do the same thing on the Smith chart and not do a single step. So 50 minus 50J is 1 minus J, right? So when you normalize it, it's normalized would be 50 minus 50J divided by 50, which gives 1 minus J. Now that's impedance Smith chart. So I represent that with on the one circle, and it's minus J. So that should be here, right? That's minus J. Now, so that's impedance Smith chart. Now if I go back to the dotted lines, light dotted lines, the conductance at this point would be what? It's not 2 because it doesn't show the both the axis. So when you have 0.25, so it goes the other way. This is, so if I it's 0.5, 1, 2, likewise it goes the other way for the admittance chart. So it's 0.5. Are you guys getting what I'm doing? So I'm trying to find, so I found the real resistance circle and the minus J, which is this one. So it's 1 minus J. Now I have this circle that is a conductance circle that goes through here, right? Initially I used resistance circle to come here. Now I want to convert it to a admittance, so I will pick the conductance circle which has a 0.5. So conductance is 0.5 Yn, and then what do I need to do to get the susceptance? So I had to look at this curve, right? And it's 0.5 J, right? Guys following me? Or confusing? You're pretty much reading off two graphs on the same, two Smith charts on the same Smith chart. Okay, because from nodding heads, I think you guys didn't understand it. Okay, so okay, let me do. So remember this number. I'm going to erase that. So this is the answer we should, at the end, should get. So if I clean this up and then go for that. So if I normalize an impedance, 50 minus 50J, and normalize means divide by 50, I get 1 minus J, right? So I'm on the impedance Smith chart, which is the the darker lines, not the dotted lines. So there are dotted lines, visible enough, yeah. So I'm in this resistive circle somewhere, that's 1, and I'm in minus J. So minus J is this reactance curve. Now you'll notice there are two terms, minus J and plus J. Now this represent, if it's minus J, the first one here belongs to the impedance Smith chart. The bottom number belongs to the admittance Smith chart. So if I go back one slide, you'll notice it's admittance Smith chart, it's J, impedance Smith chart is minus J. Okay? So because they have to represent both the numbers, that's how they do it. And you'll also notice here there's only one number that belongs to impedance Smith chart, but if I go to the admittance Smith chart, it's 0.5, 0.25, right? Because at the end of the day, the proper Smith chart will look like this. It's hard to read. But so previously, before the tools came in, the designers used to actually plot these points here and then do to decide your matching circuits and all that. I'll tell you, like, because some of the questions I think I've received is, how do you decide your matching circuit? Like, that was one of the fundamental questions you guys had, right? Because Smith chart will help you how to design your matching circuit. We'll come to that point, but to do that I have to come step by step. Now, so okay, we were doing the question. So 1 minus J, we are here. So that up to that it's clear, right? Okay. Now I'll switch back to the admittance Smith chart, which is I'm focusing on this dotted line, and that dotted line here, admittance chart is 0.5, it's not J, 0.5. Okay, and then on the susceptance semicircles, not semicircles, susceptance curves, this represent 0.5 J. So if I write my Yn, it's 0.5 plus 0.5 J, right? Same as, like, then it's normalized admittance. That means if I want to remove the normalization, I will have to divide by 50. Because impedance, I have impedance, normally impedance I will divide by 50. That means if I want to, so normalized impedance is n minus 1 minus 1J. If I want to denormalize it, I will have to times it by 50, which is 50 minus 50J, right? So to remove admittance, remove the normalization, I have to divide by 50, which is 0.5 divided by 50 plus 0.5J divided by 50, which is 0.01 plus 0.01J, right? That was the answer before we worked out doing the 1 over Zn. Okay? So now it might be hard to read off the values. We are lucky we got a value that we had the curve, but if you don't have a curve, we had to interpolate. Like, so say for example, if the question was about 50 minus 60J, so this becomes 0.60 divided by 1.1J minus 1.1J. And there's no 1.1J here, so I'm guessing 1.1j is somewhere here, like that, and I'm at this point, and my admittance curve will be 0.4j, I don't know, right? So you have to interpolate. Now with the tools, AWR or other tools, you can actually pinpoint any point and then right click and read off the value. Or when you take your mouse, it might read off your value, right? Okay, so now that's how you convert impedance to admittance in Smith chart. But this is not the use of the Smith chart. This is just trying to represent impedances and convert them to admittances and all that. Now in this course, we will cover probably the basics of the Smith chart. There's a lot more than what I'm telling you guys, right? It's probably a few hours of lectures on this. And if you are interested and you think you probably want to pursue this path, you might be worth reading off about this stuff. Now a complete Smith chart will have all these curves plus couple of scales. Now one of the scales would be VSUR, one of the scale would be reflection coefficients and all that, and this will be distance to load, etc., etc., etc. Now what you need to, you don't really need to know that for this course, but what I'm trying to say is that Smith chart will give you a big insight into the circuit. Just by reading off a point, you can probably say what is the reflection coefficient, what is the impedance, what is the admittance, because you can switch between all that. Now with the tools you can switch between because they'll do it for you. Previously we didn't have those tools, right? I mean the AWR, CAD tools. So that's the use of the Smith chart. Now, few things that we need to remember here. This is a very important slide, this particular slide. It will actually tell you how to design your matching circuit. Because you wouldn't know whether to have a L and C, whether to have a C and L, whether to have LCL. You don't know that, like when you have a circuit. So the first thing you would do is, so what I want to get out of the lecture at the end of the day is that when you have a source and you have a load, you will know what is the circuit look like, not the values, but whether it's L and a C, whether it's C and L. So you can determine it based on this Smith chart. Now I'll go back to the impedance Smith chart here. That's the impedance Smith chart. So you always travel along a resistance circle. Now when you move, so if you have a transmission line, okay, so that's a 50 ohm line, and I'm looking at impedance here, and if I'm moving towards this way, what happens is with the length, I will be going along this resistance circle, because wherever any point in this transmission line, I will see 50 ohms. Doesn't matter, right? Where am I? You guys get my point? So if it's a 50 ohm line and I'm looking at this, so that means impedance here is 50 plus 0j. That means I am here, right? What happens when you travel along that line is you will actually have your real part of that doesn't change. Well, for the transmission line, it's not really true to say that real part doesn't change, but you can keep yourself in a constant resistance circle as long as there's no losses. So when I say constant resistance circles, that's because there's no losses. If there are losses, you will drop down in the circle. We don't want to go to that complexities. We'll just stay in the. So just remember, you will always travel in a constant resistance circle. Okay. So for now, just earmark that. Now, so in a constant resistance circle, if you go that way, if you have to go that way, that means you're increasing inductance. That's because 0.25J, 0.5J, J, 2J, 4J. So increasing inductance means it's positive inductance. It's an inductor in series, right, to your circuit. So if you go that way, it's a series inductor. If you have to go that way, it's a series capacitor. So what does it mean? So if you have a 50 ohm line, so that's 50 ohm line, that's one, right, normalized, and this will be xj, and if x increases, that means you go that way. You go that way. Because if you are here at this point, it will be 1j. If you are at this point, it's 2j. If you are here, it's 4j. It will be here close to infinite j. Right? So when you travel that way, you're talking about having a series inductor to whatever your circuit. This will start to make more sense when I do a question, but just remember this at the moment. If you travel this way on the circle, you are having a series capacitor. Okay, now if I go to the admittance Smith chart, if I travel this way, it means a shunt inductor, which means if you have a circuit, 50 ohm line, you are having an inductor to the ground like that. Previously, so that's a shunt inductor to the ground. If you have to travel this way, it's a shunt capacitor to the ground. Okay? Now, I strongly recommend you guys to read the Steers reference book for this, because this will be very useful. So we have four types of elements now. That capacitor, so these are pretty much all the four elements that we can have in a circuit, right? Apart from the real resistive parts. So these two on impedance Smith chart, they will go in these two ways. These two is represented in admittance Smith chart. Okay. Now, so remember that part so far? Okay. So this is a question. So when you have, this question is on design a 2-element matching network to match a 25 ohm source impedance to a 200 ohm load impedance. So which means you have a source impedance of 25 ohms. That's 200 ohms. So when I normalize them, it will be 0.54, right? So that Z S normalized. This is Z load normalized. So if I represent them, 0.5 is here. 4 is here. Right? Clear so far? So that's our source, and that's our load. Now when you do an impedance matching, you have to, whatever the circuit that you do here, will transform that 25 ohm impedance to a 200 ohm impedance, right? And that's why, remember, we did it mathematically using those four types of equations before the break, right? Remember, you guys have determined the Q first, and then you work out whether it's a series L whether it's a circuit like series L and shunt C, or whether it's a shunt C, series C, shunt L. There's few stuff that we did like in the first part of this impedance matching. So you do that mathematically there. I'll do more questions on that in the lectorial, so you guys understand what we are talking about. Or you can do it graphically here. Now what I said before is like you always travel in resistance circle. So the way for me to go from this point to that point is either I can go up to here following constant resistance circle, then follow constant conductance circles, come back, right? Because when I do go from here to here, I'm only changing the reactance. I'm adding a reactance to this circuit, whatever the matching circuit. So remember the slide before, I said if I'm going this way, I'm talking about a series inductor. So I want a series inductor, right? So I want a series inductor, right? And then I come to a point where my constant conductance circle will go through my 4.4, which is load line, and then I go along this circle, follow constant conductance circle. If I'm going like that in a constant conductance circle, that is a shunt capacitor, right? So that's from here, shunt capacitor, because I'm following a constant conductor circle clockwise. Okay, I know that's a lot to take in because it's the first time you guys are listening to this. I didn't really understand when I was learning this initially. You have to read upon it, but someone has to tell you this stuff, right? So, and that's me. So, so that's a shunt capacitor. And then you can't come back to your 200 ohm. So a circuit actually is an inductor.
From that point, we are going down, so that's why it's a shunt capacitor.
Yes, so we're going clockwise.
Yeah.
Going down, clockwise. If it was the other way, it's a shunt inductor. That makes sense? Yeah. Okay, so you know the circuit topology now. Now you have to also find the values, right? So when you find the values, so if I'm going from here to here, you can't see the reactance curve, but in this one, that is the reactance curve. And it says 1.323J, right? So my reactance from here to here, I have to change my reactance from 0 to 1.323J. So my change in the reactance is 1.323J minus 0J. That gap. This is 1.323 because it reads 1.323. And that's 0 because that's a 0 reactance. It's a straight line. So that's 1.323 change in the reactance. Okay? Now this is normalized to 50 ohms. So you need to multiply this by 50 to get in terms of impedance. So 1.323 times 50 will give you some number. But that's actually omega L, if you remember this. That's your omega L, because this is times J, right? So your omega L will be 1.323 times 50 in here, which means depending on the frequency you pick, your L will be different, right? So, but this circuit will work for any frequency. The reactance will stay the same depending on your omega, which is say 1 gigahertz. You can do 2 pi times 1 gigahertz. Then you can find L, and that L, if you put that L and then find the right C, this circuit will work for 1 gigahertz. So it's matched for 5 ohm to 200 ohm at 1 gigahertz. It won't be working for 500 megahertz because your L is different to 500 megahertz, right? Because it has a certain bandwidth. Right, so that's how you find the L. Now, if you want to find you don't have to find the L. So I won't be testing you guys to find a value in a Smith chart. I think my intention here is for you to determine whether it's an LC circuit, whether it's a series cell, capacitive C. But I will do questions in the lectorial, okay, with sample questions with the values. So because here I'm not really doing solving the question for you guys. Here my idea is to give you the concept. Okay, so this is how you do it. Because if I don't want to confuse you with the numbers and the outcome together at the same time. Now so if you want to find C, like you can read the book obviously. If you want to find C, what you need to do is you find the susceptance here, which is 0. Minus the susceptance here, minus 0.66. So your change in your delta B is 0 minus 0.66 gives you 0.66 J. Now that's your delta B. So if you want to convert it to so your susceptance is 1 over J omega C, right? So you need to get 1 over 0.66 which is equal to omega c, then you can solve it to find the capacitance. Now, okay, we don't want to go back to that yet. The whole idea here is what is whether you have L and C, whether you have a C first, L first, or L first, or C first. Okay? Now, what if you want to match it from the load to source? So, I'm going to delete this part. You could either come this way and then go that way, right? So, if you go this way, okay, so before I go to that, you have two ways of solving this, right? Yeah. Or you can, so from, even if you're going from source to load, you could do it in this path. I follow the circle, then I follow this path. So here, if I go follow this path, this means a series cap, and this means shunt inductor. So I could have actually a circuit with a series cap shunt inductor as well. So that there will be a solution for that. So you could have two types of matching circuits for this, but you will pick one you want based on whether you want to pass DC or not. Did you get my point? Because previously I talked about this too. So you could have a, so this is a DC block, right? So if you want to block DC, you will use that, this circuit. If you want to pass DC, you'll use this circuit. Okay, now a similar question is here. I will solve this in the lectorial, this question, because of the timing. But in terms of your assessment, if you plot your, let me see if I can actually plot it. So I'll open up so in lab 2 that we did, I gave a project to tune, remember? This is the project I gave you guys to tune. Where you guys have to tune the circuit to remember this lab 2. There was a project circuit course 2x25 in there. So when you do assessment 2, you might be using 2x25, you might be using 2x50. I don't know which one you guys are using, but you can look at the, so because you want to go from 50 ohm to the impedance here at this port, right? So I can actually plot this in the Smith chart. So if I plot this in a Smith chart, okay, I'll say graph 1, and then in that I will add measurements 2x25. So S11 would be my input. Say okay, and then I will simulate that. Now that goes for a wider band, so I won't, so let's see, add a marker. That's 0.5. We are interested in 12 to 16 gigahertz, so I will actually restrict the frequency from 12 to 16. then here. So that's my 12 to 16. So that's S11 of that transistor at the gate, right? So when I want to match the circuit here, whatever the circuit I'm going to come up with, we'll need to have the conjugate of that, right? Because so then the imaginary parts will cancel out. So that means I have to plot the conjugate of this as well. I'll get the conjugate as, so when if you want to plot conjugate, you do that. So that's a conjugate, and then it will be exactly on top of it. So the way it works, if you present, so this is the impedance at the input of the gate. If you present an impedance like that, the imaginary parts will cancel out and you will end up with a 50 ohm. Now that means you have to make your whatever the matching circuit here to go from 50 to around here. Let's say we pick the center frequency 14, yeah, that's, so we need to go from 50, which is 1, which is here, to here, right? So what you should do is you should probably have a few ways of doing that. You can follow a constant resistance circle. See this constant resistance circle, and then you can go up like that, right? Is that clear? So I can't draw it on this here because it's AWR. If I follow a constant resistance circle, I'll go this way. That means a series. So what happens if I follow a constant resistance circle in this way? Series capacity.